In this video from ITFreeTraining, I will look at how to manually perform IP6 subnetting. If you have not watched our previous video on IP6 subnetting, I would suggest starting with this video to teach you the basic concepts. By the end of this video, you will understand how to calculate IP6 subnets and implement them in your organization. To understand the basics of how IP6 subnetting works, I will first look at an example IP address that an ISP might allocate to a customer. The ISP will generally allocate the first 48 bits of the IP address. The next 16 bits of the IP address are the subnet ID. The idea behind the original allocation of IP6 addresses was the customer would have the full 16 bits to allocate as they see fit. In some cases, the ISP might use some of the 16 bits rather than allocate all 16 bits to the customer. In this example, we'll assume that the ISP has given us the entire 16 bits to allocate for ourselves. For the sake of completeness, we'll show the interface ID, which will complete the 128-bit IP address. The focus on this video is on the subnet ID and the mathematics of dividing up the IP address into different subnets, so the interface ID is irrelevant. So let's start to understand some of the basic principles and mathematics behind the IP6 subnetting and how it is accomplished. You can see in this case that there are 16 bits that can be allocated by the customer. In some cases, some of the bits of the subnet ID may have been allocated. For example, the ISP may have allocated some of the bits between different customers, or the customer may have allocated some of the bits to different networks. If some of the bits have been allocated, in the upcoming formulas, we'll use F to indicate fixed. This is the portion of the subnet ID that is already subnetted and thus cannot be subnetted again. In our example, we will start with all 16 bits being available for subnetting, and thus F will equal 0. As we move through the video, bits of the subnet ID will be allocated, and thus the value of F will increase. The next part we're going to look at is S for subnet. This is how many bits we want to allocate to new subnets. The larger the value of S, the larger the amount of subnets that are created. The final section of the subnet ID will be represented by R, which is the remaining portion. This is the part of the subnet ID that has not been allocated as of yet. With IP6, it is possible to create hierarchies of networks. The R value is how many bits are left that can be used later on to create additional levels of subnets. The important point to remember is that F plus S plus R equals 16 bits. If the values F plus S plus R does not add up to 16, a mistake has been made. For an example of how to break up an IP address into different subnets, I will start by looking at how the subnet ID can be broken down into different countries. Whenever you, as an administrator, begin to develop a plan for your subnets and begin allocating subnet IDs, you're going to want to leave enough room for expansion. So, in our example, consider we have locations in the US, Canada, and England. Furthermore, we'll assume the company is not expanding to any more countries. To determine how many bits we'll need, we're going to take a look at the powers of 2 table. This table lists all the powers of 2 from 1 through 16. As it goes up, it allows more networks to be created. In this example, we have 3 countries, so at least 3 networks are required. So if we look at the powers of 2 table, you can see that in order to get 3 subnets, we need 2 to the power of 2, which is 4. This means 2 bits are required. That gives us 4 subnets. Now that we know how many bits are required, the next step is to break the original address down into subnets. To create a different network for each country, I will first take the IP6 address given to me by my ISP. So far, no bits of the subnet ID have been allocated, so this essentially means that F for fixed is equal to 0. This leaves the 16 bits of the subnet ID available for allocation to networks. The next step is to allocate some of the bits for the subnet ID. Since 3 networks are required, 1 for each country, the power of 2 table told us that 2 bits are required. This will give a total of 4 networks. So to account for this, I will allocate 2 bits of the 16. This leaves 14 bits of the subnet ID unallocated. The next step is to start working out the addresses of each network. That is, the addresses that will be used for each country. Networks in IP6 are often referred to as hierarchies. Thus, the first step of hierarchies will be referred to as the first level of subnets. The first subnet is simple to work out. All I need to do is use the address the ISP gave me and change the prefix length. This will be the old prefix length plus the additional bits used in the subnet ID. So essentially it will be 48 plus 2, giving a result of 50. The address of the next subnet is a little harder to work out. In order to work this out, first an increment value needs to be calculated. This value is added to the previous address to work out the address of the next subnet. Let's have a look at how this is done. To work out the increment value, this equation is used. It is just a matter of adding the values that we know into the equation. No bits have been allocated so far from the subnet ID, so F is 0. S is the number of bits that we want to allocate from the subnet ID. From the powers of 2 table, this value is found to be 2. This gives 2 to the power of 14, which is 16,384, or 4,000 in hexadecimal. To make things simple, I will open Windows Calculator and use it for the math. First, I will select the View menu and select the option Scientific. Different options are found in different parts of the Windows Calculator, so sometimes you need to change views to get what you need. To work out the increment value in the calculator, I will enter in 2 and press the power to Y button, and then enter in 14. This gives me the value of 16,384. The next step is to change this to hexadecimal. To do this, I will select the View menu and then select the option Programmer. I will enter in 16,384 and then select the button Hex. You can see the number changes to 4,000 in hexadecimal. To work out the next subnet is a matter of adding this value to the previous value. In this case, the value is 0, so it is simply the increment value in this case. To work out the next subnet, I will add the increment value of 4,000 in hexadecimal, giving a value of 8,000 in hexadecimal. This will be the next subnet. You can see how the increment value is used to find the next subnet. We only required 3 subnets in this example out of the 4 available. If you want to find out the address of the last subnet, add 4,000 in hexadecimal, and this will give you the value of C000. This will be the value of the last subnet. Now that all the subnet addresses have been worked out, the next step is to allocate these subnets to different countries. Shown here are the 3 subnets that have been allocated using the first 2 bits of the subnet ID. There are 4 subnets created, but we'll only need to utilize 3 to meet our requirements. The 4th will be available for use if it is ever needed. Now it is time to allocate them to the specific countries. So we'll set the first to the US, the second to Canada, and the third to England. So from a hierarchical level, now we can see that any traffic with the CAD0000 address is from the United States, and any traffic with the CAD4000 address is from Canada, and so on. Now that a subnet has been allocated to each country, we'll next allocate subnets to be used for states, provinces, territories, and that each country may have. In order to do that, we need to evaluate how many networks our company will require for additional subnets. In our example, we'll assume that the most we need is 60. We'll be heading back to the powers of 2 table again. Look at the table. We can see that for 60 networks, we would want to use 6 bits, which in the table shows 2 to the power of 6 is 64. Now that we have the number of bits required, let's have a look at what is required to break down the address in a second level of subnets. Taking the address for Canada, the next step is to work out the subnet address for provinces and territories in Canada. Remember that 2 bits of the subnet ID have been allocated. From the powers of 2 table, it was worked out that having 60 networks would require 6 bits. So an additional 6 bits from the subnet ID will be allocated. This leaves 8 bits that have not been allocated. To work out the second level subnet addresses, the process is the same as before. For the first subnet address, the address that was allocated to the Canada network is copied. Notice that the prefix length has changed. Since 6 more bits of the subnet ID have been used, These are added to the prefix length of 50 that was allocated to Canada to give 56. The next step is to work out the increment value. Like before, it is a matter of putting the value into the equation. The value of f will be 2, since 2 bits of the subnet ID were allocated to countries previously. Since an additional 6 bits of the subnet ID will be used for states, provinces, or territories, the value for s will be 6. Once the values have been put into the formula, it is a simple matter to work out the increment value. This gives the value 256, or 100 in hexadecimal. I will now open Windows Calculator and have a look at how to calculate the increment value. First, I will change the view to scientific, enter 2 into the calculator, and raise it to the power of 8. This will give the result of 256. I will now change the view to programmer. The calculator is still displaying hexadecimal values, so I will press the DEC button to change it to decimal. Once changed, I will enter in 256 and then press the hex button to convert it to hexadecimal. Notice the result is 100 in hexadecimal. To work out the next subnet, I will add the value 4100 in hexadecimal, giving a value of 4100 in hexadecimal. To work out the next subnet, simply add 100 in hexadecimal, giving the value of 4200 in hexadecimal. The process is the same to work out the other 64 addresses. In this case, I will skip a few addresses and go to the last address. Now that the address breakdown is complete, these addresses can be allocated to networks and broken down further if required. In this example, the address will be broken down one last time. For the final breakdown, we're going to allocate some bits to the offices in each region. We've determined we have no more than 10 offices in each region, so now we're going to use the powers of 2 table again. To get 10 offices, we need 2 to the power of 4, giving us 16. Now that we know that we require 4 bits, the next step is to perform the breakdown of the address. I will now take one of the addresses from Canada and add another level of networks for the offices in that region. For these networks, I will allocate 4 bits of the subnet ID. This leaves 4 bits of the subnet ID for further expansion. This does sound good. However, remember, if you wanted to add more countries later on, this would mean changing the address of each network. For this reason, if you have some spare bits left over, it is worth considering using them to add additional networks for future expansion. In this example, there are 4 networks allocated to countries. Adding just a single bit would double it to 8 networks for countries. However, having some free subnet bits also means another level of networking can be added later on if required. The next step is to work out the addresses for each of the networks. Like before, the first network is easy. Copy the previous network and change the network prefix. The previous network prefix was 56. 4 more bits were allocated from the subnet ID for office networks. This gives a network prefix of 60. The next step is to work out the increment value. Just like before, the same equation is used. The value of 8 is used for f, and the value of 4 is used for s. Once these values have been put into the equation, it is a simple matter to work out what the result is. This gives a value of 16, or 10, in hexadecimal. I won't worry about working this out using the calculator, as the value is small and easy to work with. To work out the second network, simply add 10 in hexadecimal to the last network address. The same process is done for the next network. This is repeated until the last network is worked out. You can see that there is some math involved in working out IP6 subnets. However, in my opinion, once you get used to it, subnetting in IP6 is easier than IP4. This concludes this video on IP6 subnetting. I hope you've enjoyed the video and found it useful. Until the next video, I would like to thank you for watching.